Hello friends, welcome to Engineering Funda family. In this video, I will explain VSB signal with great clarity. Before I start with my explanation, let me tell you the outlines of this video. See, in this video, first of all, I will explain basics of VSB signal. After that, I will explain VSB modulation using VSB Modulator. After that, I will explain VSB Demodulation using VSB Demodulator. After that, I will explain VSB Filter Response. And at last, I will explain application of VSB signal for TV channel. So let us start this video with first agenda, that is basics of VSB signal. First of all, you should know what is VSB. See, VSB means Vestigial Sideband. If you talk about SSBSC, then in SSBSC, we have one sideband transmission. Either we transmit upper sideband or we transmit lower sideband. In VSB, we transmit one sideband along with vestigial band. So one sideband plus vestigial band, that's why it is VSB, vestigial sideband. See, compared to SSBSC, there are few advantages that is there with VSB. So first of all, I will discuss about drawbacks of SSBSC. See, in general, there are major three drawbacks that is there with SSBSC. First drawback, that is based on need of guardband. See, when you talk about SSBSC, at that time, we need to have guardband with message signal. If you talk about voice signal, if you talk about speech signal, then speech signal that is there up to 4 kilohertz, right? And if you see the range, then that is there from 300 hertz to 4 kilohertz, that is in general range, right? Here, see, from 0 to 300, we don't have speech signal in majority of cases. So you can say from 0 to 300 hertz, we have guardband. And as in speech signal, we have guardband, we can use SSBSC, right? So in SSBSC, we need to have guardband with message signal, right? That is one drawback. See, second drawback is based on bandpass filter. There is a need of sharp edge bandpass filter with SSBSC. To get sharp edge bandpass filter, we need higher order of bandpass filter. See, in SSBSC, we need to transmit either upper sideband or lower sideband. And to have one sideband, we use bandpass filter and that should be having sharp edge. And to get sharp edge, we need higher order of bandpass filter, that is costly, right? So in SSBSC, if you don't have guardband, then you need sharp edge bandpass filter, that is costly. And third drawback, that is based on message signal. If message signal is wideband message signal, then it is extremely difficult to design SSBSC. For example, if you talk about phase shift method of SSBSC generation, then in phase shift method of SSBSC generation, we were been using 90-degree phase shifter, and that is extremely difficult to design for wideband message signal, right? So one can say, if you don't have guardband and if you have wideband message signal, then you cannot prefer SSBSC. If you have lower frequency band with message signal along with the guardband, then you can prefer SSBSC, right? So if you have wideband message signal without guardband, then you cannot prefer SSBSC. In that case, we should be going for VSB. And if you talk about DSBSC, then in DSBSC, transmission bandwidth is 2 FM. See, in SSBSC, transmission bandwidth is FM. In DSBSC, transmission bandwidth is twice of FM, right? While in VSB, transmission bandwidth is FM plus FV, some vestigial bandwidth will be there, right? So when you talk about wideband message signals like video signals, at that time we should prefer VSB, that is having lower bandwidth compared to DSBSC. It is having higher bandwidth compared to SSBSC, but Due to drawbacks of SSBSC, we cannot prefer SSBSC in wideband message signals like video signals, right? See, with VSB, bandwidth will be 25 to 30% more compared to SSBSC. But due to some disadvantages which is there with SSBSC, we prefer VSB for wideband message signals like video signals. If you talk about speech signal, then we used to prefer SSBSC, but if you talk about video signals, then we used to prefer VSB, right? Now I will explain you modulation process of VSB. Here we have message signal that we give it to product modulator, and another input to product modulator is carrier signal. So local oscillator will generate carrier signal and message signal is getting multiplied over here. So after multiplication, we will be having double sideband suppressed carrier, right? So here we will be having DSBSC's output, and this DSBSC output that we pass it through VSB filter. See, VSB filter that is having one sideband plus vestigial band, right? I will explain that frequency response in great detail in this video itself. Right now consider we have DSBSC signal that we pass it through VSB filter, and then we have VSB output, right? So here output of product modulator, that will be multiplication of message signal x of t, and carrier signal, here we are considering carrier signal to be 2 cos of omega ct, right? So this is multiplication of message and carrier, that is output of product modulator, and this is what? DSBSC output, right? Now this DSBSC output that we give it to VSB filter. VSB filter is having response that is h of I, right? So output of VSB filter, that will be convolution of input signal that is 2xt cos of omega ct and response of VSB filter that is hi of t. See, this star sign, that is a sign of convolution. It is not multiplication, right? So when you talk about time domain analysis, at that time there will be convolution of input and response, and that will be generating output, right? So this is our output in terms of convolution, but we want output in terms of multiplication. So what we will be doing is we will be applying frequency transform over here. We can prefer Fourier transform, we can prefer Laplace transform, right? It is up to you. Here I am going to prefer Fourier transform. So we will be converting this time domain analysis into frequency domain. So here you can observe, see this convolution, now that is getting converted into multiplication, right? See, in frequency domain, here convolution is converted into multiplication, right? So this convolution, now that is there in multiplication. This hi of t, now that is hi of f. And here we have 2xt cos of omega ct. So here we have multiplication of time domain. In time domain, if there is multiplication, then there are two frequency components, f plus fc, f minus fc. Here we have reference input signal, that is message. So with x, now we have f minus fc and f plus fc. Here see, we have 2. That's why here we have magnitude 1 with f plus fc and f minus fc, right? That's why I have considered 2 cos of omega ct to get normalized frequency components, right? So this is our output, and that is VSB output. And this VSB output, that is purely depending on hi of f, and this hi of f, that is frequency response of VSB filter, right? Now I will explain demodulation process of this, right? To get demodulation, here we have VSB demodulator, where input is VSB signal. So at receiver side, we have VSB signal that we are receiving, that we give it to product modulator again. Second input to product modulator is carrier signal. So but obviously here we are multiplying these two signal, and whatever multiplication is there, that we give it to low pass filter, and at last we have message signal as an output. But how we have message signal as an output? Let me derive it. So here output of this product modulator, that is y dash of t. Here I am representing that in terms of frequency domain. So what will be my output in frequency domain over here? See here carrier signal that is having frequency fc. So with y of f, after multiplication, there are two frequency components, y of f minus fc and y of f plus fc, right? After multiplication, we have two frequency components. Always remember this, f minus fc and f plus fc. So here suffix is y. So I am listing it as y of f minus fc and y of f plus fc, right? See, in my last slide, I have explained y of f, that is VSB signal. Let me place it over here again. See, VSB signal, that is x of f minus fc plus x of f plus fc into hi of f, right? Now, to get this in terms of x of frequency response, here, see with this, here we have y of f. To get y of f minus fc, in this, we need to substitute f minus fc instead of f. And to get y of f plus fc, in this, instead of f, we need to substitute f plus fc, right? So if you substitute that, then see here, first of all, what I'm doing is I'm getting y of f minus fc. So instead of f, I'm substituting f minus fc. So here we have f minus fc means f minus 2fc. Here we have f. Instead of that, I'm substituting f minus fc. So minus fc plus fc, that is getting cancelled. And here hi of f is there, where I'm substituting f minus fc. And to get y of f plus fc, we need to substitute f is equals to f plus fc. So here, see with this first term, we are having f minus fc, where f is f plus fc. So minus fc plus fc is getting cancelled. And with this term, we have f is equals to f plus fc. So here we have f plus fc means f plus 2fc. And with hi of f, here we have hi of f plus fc. So here we have in total 4 terms. Out of these 4 terms, here message signal, that is x of f, right? And x of f minus 2fc and x of f plus 2fc, that is higher frequency components. So let me take x of f common. So here you can observe, along with x of f, we have hi of f minus fc. And over here, along with x of f, we have hi of f plus fc, right? And you can observe here f of f minus fc into hi of f minus fc is there with us. And over here, along with x of f plus 2fc, we have hi of f plus fc. So if you pass this signal through low pass filter, then these are higher frequency components, right? So these higher frequency components, that is getting eliminated if you pass this signal through low pass filter. So here we will be having message output, that is this. Now question is, how can you say this is message output? How can you say this is message output? So that one can understand based on frequency response of VSB filter. So here major complexity with VSB modulation is based on designing of VSB filter. So you need to be careful when you understand VSB filter response. Let me explain that. So here in VSB filter response, we have vestigial sideband. So how we assign vestigial sideband, that you need to understand. So here on the horizontal axis, we have frequency, and on vertical axis, we have amplitude. See here, I'm taking a reference of fc, right? Here, let us consider we are having one sideband, that is fc plus fm, and somewhat vestigial band is there. So here we have negative replica. So focus over this side only. See, if you observe the response of vestigial sideband, then here you can observe, see, at fc, here magnitude is half of maximum. And over this side we have FC minus FV. So this much band is vestigial band, right? From FC to FC minus FV, this much band is vestigial band. And this is one sideband, FC to FC plus FM, right? And over this side, this is arbitrary response. So slope of this FC plus FM, that is not affecting much. You need to focus at the reference of FC only. To understand that, let me normalize this response. Normalization means here maximum value is 1. So if you observe at FC, we have half value. Now you need to understand how message signal is there. See, at message signal, if you talk about low frequencies, then information of low frequency that will be there at FC, means DC value will be there at FC. If you go in this side or if you go in this side, then gradually frequency will increase. So if you add value in terms of frequency in this direction with respect to message and in this direction with respect to message, and as if response of addition of this and this, that is unity, in that case one can easily extract message signal. If you have higher value over here at FC and as if slope is happening somewhat like this, in that case at lower frequency there will be more magnitude, but we want uniform response with respect to message signal. To get uniform response with respect to message signal, here at FC, in response of VSB filter, there should be half of normalized value, and as you go in this direction and as you go in this direction, this area and this area, see, that should be having equal magnitude, and that is possible only if you have HI of F minus FC and HI of F plus FC, that is unity. If this is unity, then there will be uniform amplitude of message signal with respect to range of frequency of message signal. So always in VSB filter response, here we have vestigial band and here we have carrier. Over this side we have one sideband. So from FC to FC plus FM, we need to see FC minus FV and FC plus FV, this much range. And see, here we have vacant area and here we have filled area. So this much magnitude and this much magnitude, that should be equal. Means normalized value with respect to FC, that should be having unit value. That is how frequency response should be there, right? And if it is happening, then at the output side of low pass filter, we were been having this response, where as if this is unity, then we are extracting message signal at output side. And always remember, usually what we do VSB modulation in TV broadcasting. So service provider that is generating TV channel signal. So that VSB signal that we all are receiving at our home, right? So that will be having this response. Now in our television, we have only low pass filter. And after passing it through low pass filter, immediately we will be getting message signal, right? Now how exactly we get it? Let me explain that by one application. So now I'll discuss about VSB signal for TV channel. See, television channel that is having video and audio signal. See, if you have only audio signal, then SSBSC is sufficient. But in TV channel, we have video as well as audio, right? If you talk about TV channel bandwidth, then that is having bandwidth around 4.2 megahertz for video. See, for video, it is 4.2 megahertz. So if you use DSBSC bandwidth, then in DSBSC, for video itself, we need bandwidth of 2 into 4.2 plus somewhat guard band plus audio bandwidth. So that will be somewhere around 9 megahertz. But if we use VSB, then in VSB, we need one band, then vestigial band, and then audio. So that is somewhere around 6 megahertz. So here we are saving bandwidth of 3 megahertz for one channel. But in TV, there are so many channels, right? There can be more than thousands of channels. So if you talk about 1000 channel, then with 1000 channel, how much bandwidth that we are saving? With 1000 channel, we are saving bandwidth of 1000 into 3 megahertz, right? Means somewhere around 3 gigahertz of bandwidth that we are saving using VSB, right? That's why we don't go for DSBSC. SSBSC is not possible. So in TV transmission, we need to go for VSB only. Now let me talk about how exactly response will be there. So here I'm talking about response with respect to one channel, and that is normalized. So here I'll be talking about that response in terms of megahertz from 0 onwards. Practically we don't transmit TV channel from 0 megahertz onwards, right? That is just a reference from 0. So from 0 here, if you talk about video carrier, then reference is there at 1.25 with respect to 0. See this 1.25, that is there in terms of megahertz over here. And see video band, that is appearing like this. So this is what carrier, right? Here we have carrier. So in this side we have vestigial band, and in this side we have one sideband, right? So this much is vestigial and this is sideband. So from 0 to 5.75 we have picture carrier, and in between 5.75 to 6 here we have sound carrier with the band of 50 kilohertz. So picture plus sound, that is resulting into in total one channel video signal, right? The reason is along with picture we need to transmit sound as well. So that is how we are transmitting one channel for television, right? So this is how basics are there with VSB signal. I hope you have enjoyed this. Still, if you have any confusion, just place that in comment section. I'll be happy to help you. Thank you so much for watching this video.